Hello, everyone. So I think this is the perfect time for us to start talking about Minkowski geometry. To be honest, I have been deceiving you for quite a while now. Although this series so far discusses about special relativity, we haven't really talked about the domain of Lorentz transformation and its subsequent consequences. Basically, we haven't really entered the realm of special relativity. Yet we have passed 4 videos now. So right now I'm gonna just jump in and start with the principles of relativity and Lorentz transformation. Now, the Euclidean geometry that we talked about is essential for a reason, and the reason is it's also connected to a principle of relativity. And that principle was called the Galilean principle of relativity. Let me write that a little neatly. Galilean principle of relativity. And this principle basically says that two inertial frames, that means two frames where there is no acceleration relative to each other, basically no acceleration at all, two inertial frames in relative motion with respect to each other holds the physical principles the same in both of the frames. Now, when we move to the principle of special relativity, we carry out the same principle from the Galilean principle of relativity. Now, there is another postulate beside this one in Galilean postulate of relativity, and that is number 2, that time flows uniformly everywhere. Now, this is a very important one because normally in the Euclidean geometry or Newtonian mechanics, we do not talk about the flow of time. It's implicitly implied, and basically this is something that we take for granted. Now, in principle of special relativity, the first principle is the same, and that is that physical laws have the same form in all inertial frames that are in relative motion with respect to each other. But now we have a second postulate that says the speed of light is uniform or constant in all inertial frames. Now, as we'll see, that this will make a lot of difference, and these two together will determine the fundamental difference between the Newtonian world and the Minkowski geometry. And this starts with describing, in other words, jumping forward to the Lorentz transformation of coordinates. Lorentz transformation. Now, if we have two inertial frames, let's call them S prime and S, and they're moving with a relative velocity with respect to each other. Let's say from the perspective of this frame, this one is moving at velocity v, and the coordinates here are z prime, y prime, x prime, and x, y, z. That means we have oriented our coordinate system in such a way so that the relative velocity is along the x-axis, And also as a fourth coordinate, we have time, t here and t prime here, but we'll do something better. We'll call this one ct and ct prime. And the reason for doing this is that this brings time in the same footing, at least dimensionally, as the rest of the coordinates, which are special coordinates and have the units of length. So if this is the case, then the Lorentz transformation becomes simply x prime is equal to gamma times x minus beta ct, where gamma is a function of velocity, written as 1 over 1 minus v squared by c squared square root, and beta is simply v over c. So using the definition of beta, we can rewrite gamma as 1 over square root 1 minus beta squared. And now we have ct prime equal to gamma times ct minus beta x. And the rest of the coordinates do not transform in this way. They're of the simplest transformation. Y prime is equal to y and z prime is equal to z. And so if we rename these coordinates in the following way, so that ct becomes the zeroth coordinate x0, and x is x1, y is x2, and z is x3, then we can write them in a little bit neat way. So let me write them down. I'll write this one first. So we have x0 prime equal to gamma times x0 minus beta x1, and x1 prime is equal to gamma times x1 minus beta x0, and then x2 prime is simply x2, and x3 prime is simply x3. And the advantage of writing Lorentz transformation in this form is that this shows us in absolutely the simplistic way the symmetry of the transformation. If you allow me to compare this to the Galilean transformation of coordinates, they're simply like this. T prime is equal to t, then x prime is equal to x minus vt, and y prime is equal to y, and z prime is equal to z. So now you can see the contrast between the transformation rules in special relativity and the transformation rule in the Galilean relativity. You'll notice that the time component is independent of the special components, but that's not the same as in special relativity. Now, 2 points are to be noted in progress, one by one. Number one, this Lorentz transformation here will allow us to define what we call the 4 vectors. In this particular case, we'll define the position vector just simply by writing x. 4 vectors would be any geometric object with 4 components: a0, a1, a2, a3, that transforms like the position vector here. So a0 prime would be gamma times a0 minus beta a1. Of course, the a1 component is actually the contribution along the x-axis. And then we have a1 prime equal to gamma times a1 minus beta a0, and a2 prime would be equal to a2, and a3 prime would be equal to a3. So any object with 4 components that transforms like the position 4 vector transforms in the Lorentz transformation would be called a 4 vector. The second point I'd like to make is that how compactly and how in different ways we can write the Lorentz transformation and what are the advantages of those. So first of all, we can write in the matrix form, and that is x prime, which is a 4-vector, is equal to the Lorentz transformation matrix, which we write by lambda, acting on the 4-vector x. And if we write it down explicitly, we have x0 prime, x1 prime, x2 prime, x3 prime equal to, here we have the unprimed 4-vector x1, x2, x3, and the transformation matrix that we have, particularly in this case, is interesting. Here we have gamma minus gamma beta, negative gamma beta, gamma 1, 1, and 0 in the rest of the places. In component form, i.e. in tensor indices, we can write the same thing as x mu prime. Notice that I'm using a mu because I'm denoting space and time, both of them right now. So mu here will range from 0 to 3. X mu prime is equal to lambda, and then I have mu, I have nu, and x nu. Notice that this particular Lorentz transformation is called boost along the x-axis. We can have similar expression for boost in the y-axis. So let me just write that down. So for boost along the y-axis, we have x0 prime, x1 prime, x2 prime, x3 prime. I should write a prime here. And the transformation matrix should be gamma 0, negative gamma beta, 1, 0, 0, negative gamma beta, 0, gamma, and 1 here, and 0 in the rest of the places. Y-axis. So write down the boost along z-axis at your own endeavor. I think that will allow you to sharpen your skills or refresh your memories. Now, I must be honest, I have skipped one thing, is that the boost is only one kind of Lorentz transformation. And there is another one that I haven't mentioned, and that's actually the one you already know, that is the rotation. And this is because we have special coordinates, 3 spatial coordinates and 1 temporal coordinates. So if we do not have relative velocity with respect to inertial frames, we can still rotate the axis with respect to any direction, and that will be rotation. For example, in this case, the Lorentz transformation matrix would be 1, 1, and then simply cosine theta and minus sine theta, cosine theta, and 0 in the rest of the places. And this is the rotation with respect to the x-axis. So it's really the boost and rotation that make up the complete group of Lorentz transformation. In the next video, I'll be talking about rapidity parameter and the inner product of 4 vectors, and that will precisely give us the geometry of the Minkowski space. See you on the next video.